get started with my talk now. I'm going to be speaking about embedded domain-specific languages for embedded programming. Don't worry if you're not familiar with some of those terms, I'll go on to discuss them a bit. A little bit about what I work on. So I work at a company called CodePlay in Edinburgh, Scotland. We work on heterogeneous systems, where you might have your CPU and maybe GPU, some other accelerators, and you want to be able to program all of this stuff with a single programming model, so you don't write some code for your CPU with this programming model and some for your GPU like that. So we're working on compilers, debuggers for these systems. LLVM is just everywhere at the moment in pretty much everything that we do. Work a lot on standardization in ISO C++, and also for groups like the Kronos group who standardize OpenCL and SYCL. And at the moment, we're very interested in getting C++ running on the GPU. So you can just program C++ and have some of your computation offloaded to the GPU. So if you're interested in this stuff, come and talk to me about it afterwards. This is the view from our office of Edinburgh Castle, which is the view for some people. I have a view of a grassy embankment, but people at the other side of the office get this. It's quite nice. But today I'm not going to be speaking about what I do at work. This is something which I kind of have a outside interest in. But this is my aims for this talk. I want to try and convince you of these points. The embedded domain-specific languages can help improve the expressiveness, performance, and diagnostics from your code, and to try and make you consider maybe using EDSLs for your current projects or future projects, how you might use them, how they might help you, and then to maybe consider how C++ as a language and for the standard library, how we can improve the current state of things for embedded domain-specific languages. So these are the main things I'm going to talk about. I'm going to give a kind of overview of the idea of abstractions, particularly how we talk about abstractions in the C++ world. I'm going to go on to define like what is an embedded domain-specific language, give some examples from C++, and hopefully show how they fulfill the aims which I just talked about. I then have a case study for mechanical keyboards. Can I get a raise of hands? How many people use a mechanical keyboard? About maybe 25% of the room or something. That's pretty cool. And then I'll talk about how the future of C++ might go to support some more of these idioms in C++ 20, 23, 26, so forth. So I'm going to talk about abstractions. Before I get started, if you have any things which you need clarified during the talk, please raise your hands, but leave any longer questions until the end or until the Q&A panel, which is later on. Abstractions. We hear this phrase quite a lot in C++, I think. What do you think about how you feel when you see this phrase, zero-cost abstractions? Who feels good? Who thinks this is a positive thing? Raise hands. Pretty good, half the room. Who has negative feelings about this or any of the connotations? We have some very strong feelings from Stefan. So it's interested, the people who have negative feelings about this, what makes you feel that way when you see this? Anyone? So you realize that the zero... Yeah, so your zero-cost abstractions are not actually zero cost. So this is a possible definition of a zero-cost abstraction. Abstractions which provide only benefits. So this seems like a good thing, right? Maybe realistic, probably not. Maybe a better definition would be this. Abstractions which cost nothing so long as you forget about compilation times, debug performance, maybe debuggability. And some people do care about debug performance. Like if you're a games programmer and your debug build is running at 2 frames per second, then that's not going to be good. But I mean, this is not zero cost, obviously. We have costs in here, so maybe these are low-cost abstractions. Maybe zero-cost abstractions are one whose costs in compilation time and debug performance are outweighed by the gains we get in expressibility, maintainability of our code, the ability to write code which is at a higher level and has less bugs. But if the cost is outweighed, then surely this is a negative cost abstraction. We can then take this idea even further as abstractions which improve expressibility, maintainability, and the performance of your code in release builds pretty much entirely. So I do think that this is something which is possible in C++. C++ it's all about strong, cheap abstractions. It's, I think, one of the best languages in the world for building abstractions which allow expressive code which is fast. So that's my overview of abstractions. So I'm now going to get into embedded domain-specific languages, which is the main concept of this talk. A domain-specific language is a programming language which is focused for some application area. So for example, SQL, the database language, is made just for doing database queries and manipulation. You wouldn't necessarily write a Fibonacci sequence algorithm in SQL. Maybe you can, I don't know. Maybe it's Turing complete. But yeah. But this isn't the main idea of SQL. The main idea is to just do database stuff and do it as well as it can. Similarly for things like Dot, which is a markup language for images as part of GraphViz. We have Logo, like the little turtle language where you can draw things on a screen. And things like Verilog, which, how many of you use Verilog? Okay, so I'm in the embedded conference, definitely.
Nobody uses Verilog in Europe.
VHDL everywhere, right, yeah. Whereas a general purpose language is one which is broadly applicable over many different application areas. So C++ is a general purpose programming language. You could use it for databases. You could use it for writing Fibonacci sequence algorithms. You could use it for essentially anything. And the same goes for Java, Python, Common Lisp, Ruby, any kind of mainstream language we can just apply over many different application domains. Embedded domain-specific languages kind of put these two concepts together. So we have a domain-specific language, and we embed it inside a general-purpose host language. So my first examples on this slide is SQL and C++. So this is what SQL embedded inside C++ looks like. This is a C++ library for SQL, and as you can see, it looks like C++. It is C++, but it also reflects SQL very nicely. We're updating some database, we're setting some values, we have some predicates, and so this is a domain-specific language for manipulating databases hosted inside C++. And this is quite powerful because if we make a mistake, we do something which isn't valid or shouldn't generate valid SQL, then we can actually get a diagnostic at compile time. Whereas if we were using some runtime interface into SQL from C++, then we would only get an error at runtime. And compile time is better. Why might you want to use EDSLs, embedded domain-specific languages, for embedded programming? So generally, embedded systems have a very specialized application domain. We have applications we're writing for a very specific purpose, which are going to be running on small chips doing one thing. And we often have very strong constraints on binary size, RAM usage, performance, all of these things. We care about the kinds of things we're paying for with abstractions. But EDSLs allow us to write clear, maintainable, well-designed code without sacrificing the precious resources that we really care about. Maybe a tagline for EDSLs could be, you can write code at the level of your application logic whilst conforming to tight system constraints. So writing code at the level of your application logic means instead of taking our business logic, whatever our application is actually supposed to be doing in our domain, and trying to express it in C++ in some fashion, we're trying to raise C++ to the level of our application logic. and make it such that if you have knowledge of the application domain, maybe you don't even know C++, but you can still kind of understand what it's doing because it's expressed at the correct level of abstraction. So as I said, these are my aims. So I've got some examples of EDSLs in C++, and hopefully I can show that these examples can help with all of these things: expressiveness, performance, diagnostics. So this is Boost MSM. This is a library for writing state machines. So as you can see, it's expressed in C++ templates. We kind of encode our state machine using these templates, and you can see this is like a table. This is it's not normal C++ as we might write it from day to day. This is a domain-specific language embedded in C++. And because this is all at compile time, the compiler can actually, well, the library can generate efficient state machines from this description because all of this is known at compile time. But not all EDSLs have to be expressed in this kind of template fashion. Here's another state machine library, SML. Who was at the workshop for SML yesterday? Great, quite a lot of us. So I don't really want to give the overview of what the entire day of the workshop, which Chris gave, which was excellent. But Boost SML is doing a similar thing to MSM, but it can actually generate more efficient code. You can swap out the front end and the back end. It's more flexible, maybe even more expressive as well. So hopefully you agree that this is better than writing a huge bunch of if-else statements or handcrafted switch statements, which are just going to end up being an unmaintainable mess, and you're going to make a mistake, and you're not going to get the right diagnostics because the compiler doesn't understand you're writing state machines. It just understands you're writing some code. This way we can tell our compiler what it means to make a mistake in this DSL, and we can diagnose the issues at the level of state machines rather than at the level of C++ templates. And we have to pay for it. What are we paying for? Yeah, so you will pay for compilation time generally, although I understand that SML has pretty good compilation times, Chris. Definitely better than MSN anyway. So of course, usually with these kinds of techniques you are paying in compile time, but you're paying that, as I said, for the benefit for the other benefits which it gives you in expressibility and diagnostics and performance. Learning curve as well. Yep, yeah, there is. And if you know C++, then you can probably write a state machine just in if-else statements or whatever. You do need to learn this library, and that is a cost. Yep. So this is dlib. This is a library for machine learning. So we're here expressing all of our machine learning logic inside templates. And this looks a bit hairy. But because this is all at compile time and the library knows about it, it can generate efficient code without having to do everything configured at runtime. Boost Spirit. Does anyone here use Boost Spirit in their libraries? Quite a few. So this is a parsing library. A lot of parsing tools like Flex and Bison and whatnot, they are domain-specific languages in themselves, but you kind of have this external tooling which you have to bring into your build system to say, okay, I have a description of the grammar for what I'm trying to parse, and then this is going to be translated by some other tool into C or C++ or whatever. Whereas here, we're actually expressing directly in C++ what we want to parse. So for example, this parses a literal employee, an opening brace, and then age, surname, first name, salary. So it could parse something like that on your right. So this is quite expressive as a embedded DSL. It has a lot of features and hooks into a lot of other Boost libraries quite nicely. This is a very, very powerful abstraction for writing parsers without having to use external tools, being able to use like the entirety of the C++ language in order to write your parsers. And you definitely pay for it in compile times. This is something we work on at CodePlay. So this is Vision CPP, DSL for computer vision applications. And so we express a kind of graph of all computations which we want to carry out. And as some performance figures here, so OpenCV is the one which everyone knows for computer vision, right? And OpenCV, all of its kernels are very, very heavily hand optimized. Like, people spend a lot of time getting these things right, making them as performant as humanly possible. And in some cases, the versions we can write in Vision CPP without this crazy handcrafted kernels can outperform. And the reason is we have more context. We can actually take operations which would be expensive, such as doing round trips to your GPU by sending data over there, and then doing your computations and then sending data all the way back. Sending data to GPUs is super expensive. So if we can actually take a bunch of expensive computations and fuse them together into one operation, we can avoid going back and forth. But we can only do this if our compiler, if our libraries have all the context which they need in order to fuse these operations together. And that's what the abstractions are actually providing us. So this is a case where we have an abstraction, something which is making our code more expressible, easier to debug, and is also gaining us performance without us having to put all of the effort into handcrafting these kernels. So those are the examples of EDSLs which I had. I'm now going to go into my mechanical keyboard. So I built a mechanical keyboard. It's very, very colorful, looks kind of like sweet marshmallows, whatever. But I got all the plates were custom made. Here's them when they arrived. I got some custom switches ordered. These are called Zelios, with the nice purple stems. And then hand-wired the entire thing. This controller is a Teensy2, which is running an Atmel chip. And this is what the final result looks like. So I'm going to go into a little bit about how mechanical keyboards work. For people who deal with electronics, this is going to be super simplified, so please don't shout at me. This is what a mechanical switch looks like on the inside. So as you can see here, we've got some contacts which are currently apart. And every switch in the keyboard, everything attached to a different key, essentially forms a circuit with the microcontroller. So when these contacts are apart, then the circuit's open and no current's going to flow through there. As soon as we press down the key, then these contacts close and a circuit is formed, and this is how we actually detect key presses in mechanical keyboard. So if we raise it up, no key press, put it down, contact. So if we want to scan our keyboard to see what keys have been pressed, we do something like this. So imagine a very simplified 9-key keyboard. What we'd have is it's wired together in a matrix. So all of the switches are attached to some pin, which forms a row, and some other pin which forms a column. So see here we have A, B, and C are our rows, and X, Y, and Z are our columns. So if we want to scan to see if switch 1 has been pressed by the user, we activate pin A here, and we see if we get if pin X is active. And if it is, then the contacts are closed, and we have a circuit, and we can say, okay, yes, there was a key pressed. And if not, then we're not going to get anything. So once the user presses down the key, we're going to get this out and we can then report that over our USB protocol. And then similarly, we scan the next switch, repeat, 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 keep on going until it's unplugged or whatever. So I wrote this thing, the embarrassingly templated keyboard framework. When I was first getting into mechanical keyboards, I looked out there to see if I could write my own firmware. What would I have to do? What kind of resources were out there? And there's a huge community devoted to this stuff. But most of the frameworks for building your own keyboard firmware are written in C, and they have macros everywhere. And if you make a mistake, then you don't actually know until you plug your keyboard in, and something doesn't work, and you don't know what it is. These things are really difficult to debug. So I had the thought, what if, instead of writing everything in these pre-existing frameworks, what if I could write my own thing? And it's going to have templates everywhere, and it's going to be great. So some of the features of my framework, it does have templates. It's all C++ 17, so I use a few C++ 17 features like fold expressions for actually dealing with the ridiculous quantity of templates. No macros! Yay! So I completely got rid of all of the macro stuff which plagues the C frameworks and replaced it with templates. We also have, at least I feel it's a human readable abstraction. I think that I could give my descriptions for how the keyboard firmware should work to someone who doesn't know C++, and they should be able to understand broadly what's going on. I also have more fold expressions than real code, even more templates, and more templates. So I'm going to talk a bit about how the framework which I wrote helps to improve the expressiveness compared to the other frameworks which are out there. So this is a popular C-style framework called TMK. This is the one where, if you're just getting into mechanical keyboards, you say, oh, I want to write my own firmware. People say, okay, yeah, use TMK. It's good. And it is good. But it kind of looks like this. This is how you specify, because of course, keyboards aren't generally a strict matrix like I had. We have kind of staggering of the keys. So there are some holes in the matrix layout, and we have to have some way of expressing that. So you can see there are a few gaps in this description here, and this is how we tell the framework where there are gaps in our matrix, so that it knows not to scan for those keys because they don't exist. When I was first writing my firmware for this keyboard, I made a mistake, and I left out one of these keys, and it compiled, and it just did the wrong thing. I had no idea what was going wrong. So this was the main reason that I decided to write my own one, because I thought, you can check this at compile time. You have all the information available that you need in order to diagnose that the user has missed out a single key or something, because you know exactly how wide the matrix is going to be, how tall, and if something is missed, then you can say, you have missed something, you did something wrong, here's why. So that's very powerful. This is some more of the C stuff. This is okay. This is how you you specify your keyboard, how the characters are actually mapped on your keyboard, and this is fine. I mean, it is macros. If you miss out one of those backslashes, then compiler's going to shout at you. But hey-oh. This is how you do the matrix scanning code. It's not great. You have to manually write all of the code to activate and deactivate your pins. You need to make sure you don't make a single character mistake, or your keyboard's not going to work. And this won't be checked by the library or the compiler or anything. You can happily make a mistake, and you won't know about it until you plug it in and it just does the wrong thing. So my C++ framework, I mean, I also missed some things out from the C version. This was quite heavily stripped down. But this is almost the entire configuration file for my C++ version. So you specify which pins your rows are connected to and your columns. This is where are the gaps in my matrix in this key positions type list. And then you have your actual keyboard layouts at the bottom there. So how do we feel? Does this look understandable? Nods? Thumbs up from Odin? So this, I'm sure you agree, is far more expressive than this, or especially this. So this is given us quite large gains in expressibility. So a bit about how it's actually implemented. So if you're doing everything at runtime, you would loop over all of your matrix cells. You would work out if there actually is a key there, which we need to test for. And then you would send the current down the row, check if the column's active, and record key presses if there was any. One of the problems here is this top line. For each matrix cell, if there is a key there. This is a conditional branch which we're making every single time we're going around our matrix, and we're doing that like all the time to record all our key presses. So maybe there's some ways your branch predictor can help you there, but in the end you're going to be making a lot of conditionals where you actually know all of this at compile time. So instead what I do is I build up a list of all of the valid row column pairs, the ones where there actually is a key and I know there is, and then I generate code to do all of the actual scanning of that key. So at runtime, I'm not making decisions about whether a key's there, whether a key's not there. I already know. I've just generated the code. So this is how some of the code looks for the generation. So if you're not that familiar with templates, this might look a little bit scary. It's even more scary if I don't have these comments and I have the actual code in there. But the basic idea is I want to do pattern matching on what the user puts into this key positions. So I'm going to match up my rows and columns, and if there's a 1 there, I want to build that into a list, and if there's a 0, I just want to forget about that pair and never generate code for it. So what I do is I use partial specialization of templates. You can see the row 1 and row 0 in the second and in the first and second partial specializations, and this is how I do the pattern matching. So if there is a key there, then I'm going to add it to some compile time list and then recurse. And if there's not, then I'm just going to do nothing and keep on going down, checking all of the possible key locations. And then I need some base case to terminate the recursion. So this is all executing at compile time, building up a list of all the possible keys that we need to generate code for. This is the code for actually powering up and down the pins. So again, we take the pin as a non-type template parameter. So we know what code we're going to be generating for this pin at compile time. We can then get some information, such as the memory locations we need to read and write in order to actually set things. And we do that at compile time. You see this constexpr info. Means this is going to be happening at compile time. We're going to know what this info.ddr and info.port are when we're generating our code. So this is kind of, we have control over the loop unrolling, kind of. Yes?
The pin, is that just a type def, or is that actually?
It's a simple struct, so it's a literal type, so it can be passed around quite easily at compile time. So this is using all that we know at compile time in order to generate the actual code for doing the scanning. So that's how I think that the expressiveness is improved. a little bit about the performance. So the mechanical keyboard isn't maybe the best example for performance because we're not really bound by how fast we can scan over the matrix. Like, we're sending data over USB back to our machine, and that's going to kind of dominate pretty much everything. But a lot of the concepts do actually map very nicely to other DSLs. So the main gain that we get is we make decisions at compile time. So I talked a bit about this for deciding whether to scan for a key or not. If you know at compile time, then you can eliminate these conditional branches from your code. Like, they're just not going to be there. Whereas if you're having to check it every time at runtime, that's going to cost you something. So this is an area where our abstraction is actually gaining us performance because we don't have to make these decisions at runtime anymore. The non-type template parameters, we can get really tight control over constant propagation because if something's going to be in a context per context, then it has to be done at compile time. We know that the compiler is going to be able to optimize this because it has to by the rules of the language. Something which isn't very applicable to mechanical keyboards, but as I mentioned for the vision library which we develop at CodePlay, you can coalesce operations together if you have all of that context at compile time. A bit about the compile time and binary size. I compared my C++ version to the C version. It's not a fair comparison because the C version has some more features which I don't support. But for what it's worth, my library compiles about as fast as the C one. The binary size is actually smaller. So when people say, don't use Faraday templates, you'll just bloat your code, it all disappeared. Pretty much everything just gets disappeared by the compiler. Debug builds. I did not check. Probably quite larger. Quite a bit larger. Yeah, yeah. So diagnostics. This is actually the part which I'm most interested in. How do we generate good diagnostics for these EDSLs at the level of the application logic? So here's how we can actually validate some of our keyboard at compile time. So we can, if you're not familiar with this, this line here is a fold expression, which is a C++ 17 feature. So we can validate all of the layouts which we have in our keyboard by just generating code to do all of these static asserts. So at compile time, if we make a mistake and our layouts don't match the number of rows we said which they should in the description of our keyboard, then our compiler is going to say a layout has the wrong number of rows. It's not going to give you some esoteric compiler error which you have no way of actually tying back to your original code. It's going to say a layout has the wrong number of rows. And if you know your application domain, then you know what that means. And you can then go and try and fix the problem. Yeah, so the question was, do you get information about which row might be wrong in the compiler error? You don't, and I'm going to come to that later when I talk a bit about how we can support this better in future versions of C++. Does anyone recognize what film this is from? No, it's 500 Days of Summer, which is like a indie rom-com from 2000 somewhere. But I really like this scene where on the left-hand side we have the character's expectations. You know, everything's going well, he's happy, he's talking to someone. And then on the right-hand side, he's dejected, standing on his own with his beer. Sometimes reality does not match our expectations, both in relationships and in C++. So this is my kind of ideal. If I could, if I was a compiler and someone gave me this code to compile and I was feeling really happy that day, I wanted to be nice to my user, this is what I would tell them. I would say, here's the file you made a mistake in. The error was that layout 2 had the wrong number of rows. I was expecting it would be 4, but you actually gave me 3. So this is a little bit more more useful than what we had of just, oh, a layout has the wrong number of rows. This is because then the user has to go away and understand exactly which one they made a mistake on, which is fine. Like, it gives you a lot more information than you would otherwise have. But being able to see, oh yes, this is where I've made a mistake, this is the line you made a mistake on, is really, really powerful, and for debuggability, for developer productivity, all of these things. So that my desire is to give the user minimal information on what mistake they made and where they need to look in order to fix it. Maybe I can tell them how to fix it, but that's going to be more complex. This is kind of the minimum that I'm really looking for. This is reality. It's not great. It's actually better than the C version because at least I got an error. And you can't see it down here, but it is saying static assertion failed, a layout has the wrong number of rows. It's hidden in this just spew of templated nonsense. There are ways to get around this. Actually, I was talking to Chris about this yesterday, and one thing he said was you actually have to design your library around getting good diagnostics, which don't have all of this guff in the compiler errors. And I think that's a bit of a shame. I want to be able to have good diagnostics from having good support from the language in order to build these embedded DSL.
Kennen Sie eigentlich das Bochumer Institut für Technologie? Nein? Dann heißt es jetzt Ohrenspitzen. Denn wir machen Ihre Ideen zum Erfolg. Wie? Wir stellen Ihnen geeignete Forschungspartner aus Hochschulen und Universitäten zur Seite. Projektpläne, Förderprogramme, Antragstellung, auch das übernehmen wir. Lassen Sie sich diese Chance nicht entgehen und starten Sie mit uns durch.
Embedded domain specific languages in the future of C++. So just to get a handle, who keeps up to date with committee mailings and papers and whatnot? Okay, maybe about a fifth of the room or something. So C++ is, as you maybe worked out, moving way faster than it ever has. So the latest paper mailing for the standards was over 100 papers, and this is happening like consistently every single meeting. There are just 100 or more papers to wade through and to understand and to converse about and to try and fit together in some cohesive way so that we don't have a language which is just a bunch of different things fused together. I mean, C++ kind of already is that, but we don't need to make it worse. But there are a few things which I think would help if we're wanting to write EDSLs in C++, how we might be better supported by the language. I think most of the problem is in the diagnostics. So C++ templates are really, really powerful for actually generating fast code and having a lot of control. because it is a full Turing-complete language embedded inside a Turing-complete language. So we have all the power we need to generate good code. And I think expressibility is mostly there as well, with things like expression templates, which are used in Boost SML or Boost Spirit. Then we can have fairly expressive DSLs embedded inside C++. And so I think these things don't need a whole lot of work done to help them, but diagnostics definitely do. One thing which I would quite like is some kind of programmable compiler errors. So one of the problems with static assert, is anyone not familiar with static assert? A few people. So static assert is a C++ 11 feature which allows you to say, if this condition is false at compile time, then emit this diagnostic. So that's what I use for here. I have a static assertion which says if the size of this rows parameter pack is not the same size as the rows I get from somewhere else, then I emit this diagnostic. One of the problems here is that, as Ben pointed out, this is just saying a layout has the wrong number of rows, and I want to get a little bit more context. But this has to be a string literal. I can't use a constexpr char array or build up some kind of diagnostic at compile time. It just has to be a string literal. That's how the standard says it has to be. So there's a paper, you can see the link here, P0596, which has this constexpr assert, and there's also a constexpr trace. So constexpr assert here takes a Boolean condition and a bunch of values. And it's kind of similar to static assert in that we say this, we have this condition, and then we have some diagnostic which we want to emit. But these values can be anything. Like this is a variadic template, so we can pass anything in here, and hopefully the compiler will be able to display some information. So I can say incorrect number of rows at layout number, and then give the layout where the mistake was. I think this would be possible if we had something like constexpr assert. Yes.
Does the proposal also include that it actually shows which numbers this is comparing in this bool condition, or is it just a library feature that shows the bool there and you only get the false bit there? Because any testing library which recently tries to do this would then say 3 == 4 in the error message, which is the computed values of each operand.
Right. So the question was, in the message which this is going to be outputting, will I get something similar to so unit testing frameworks like catch or something like that? If an assertion fails, it will say assertion failed, expected 4 got 3 or something like that. It'll show you what it compared in order to for the assertion to fail. So the proposal doesn't specify anything about how the diagnostic should be emitted. That would all be down to the compiler. So a sufficiently advanced compiler could maybe do some analysis on this bool argument and maybe say, okay, well, this is a simple equality check and it failed, so I can say what the left-hand operand was and the right-hand operand, and maybe a compiler could do that. But that's more of a tooling issue rather than something which the standard is going to specify. Does that answer your question? Cool. So I don't know what the current state of this proposal is. Yes, Wouter?
In my experience, the bigger problem with assert is that it directs the user to the assert line.
Right.
Then that's no problem. The problem of one context higher.
Yep. So the comment was usually the real problem with static assert is that you don't get a diagnostic where you needed it. You get it kind of a level below in the implementation, and actually you want a diagnostic saying you made a mistake here, not a static assert failed when I was trying to instantiate your template or whatever. Yeah. So I'm not sure if this would go much to solving that problem, but maybe that's a tooling issue as well. If a compiler can actually work out the best place to display an error message.
You have to specify somehow how many levels up
Yeah.
the error should be, and there's no place in there to specify that.
Yeah, that's going to be a problem. I think, yeah, that's a good comment, I think.
Also like extend this to pass on an operand, any of the operands, and then it would look at the place where this operand, for example, is defined, and give it into there, and then you would have some control.
So the comment was you could make it aware of where the operand actually came from and use that in the diagnostic. So that might be a good way of the compiler actually working out where is the level of intent that I need to diagnose at, rather than where is the implementation detail which went wrong. So yeah, that might be an idea. Does anyone else have any ideas on this? I like these ideas.
The other possibility is to use concepts.
Yes.
Fix the error at the tablet implementation level.
Yep, so you could use concepts, and so I could have a keyboard concept, and if my keyboard, if the struct which I pass in to this template does not conform to the keyboard concept, then I will get a diagnostic. Yeah, at the right place. It will say, what's the message that the implementation gives? I can't remember. The constraint failed or something, and it will tell you what the constraint was, and it will show you where you made a mistake at the interface level rather than at the implementation level. Stefan? Okay, does anyone have any other ideas about static asserts and how we could solve some of the problems with them? Ben?
I did have, how much time did you try to spend to improve the template SPU in your area? In particular, there's a lot of compilers will make the error message somewhat more readable if you have a namespace level type depth. And I'm wondering if you tried that or any other kind of technique.
Yeah, so I tried a few techniques. There are also things you can do in order to make it that you get a linker error, and that will give you less mess than the compiler error will. So there are a bunch of techniques that you can... This is Windows Update.
It's just Windows.
Yeah. Yeah, so there are a number of tricks which you can use in order to try and cut down on all of the noise somewhat, but they do get quite esoteric quite quickly. I mean, more than template metaprogramming is already esoteric, which is quite a lot. So I don't know the current status of the constexpr assert proposal, but I think it should be a useful feature, especially so the reason it's constexpr assert rather than like building upon static assert is you could put it into a constexpr function, and if it's called in a constexpr context, so if it's called at compile time, then the condition is checked and you'll get a compile time diagnostic. Whereas if it's called at runtime, because constexpr functions can be called at runtime or compile time, if it's called at runtime, then it's kind of a no-op. So I think that solves one of the main problems in writing constexpr functions, where we can't really get... excellent. I'm just going to make sure I switch slides every now and again to... Yeah, so it solves some of the problems of diagnosis inside constexpr functions, which is quite nice. Constexpr strings. So there's been a number of proposals to try and help us build up strings at compile time, and some foundations to lay in order to actually build these concepts up. So this is a proposal which I believe has been accepted for C++20 of allowing string literals as template parameters. So we have this autoref stir, and when we're instantiating f, we're passing in a string literal, and this is going to end up as this template parameter stir. So we can use this as a kind of fundamental building block for manipulating strings at compile time. But currently, without things like this, it becomes difficult. Chris talked a little bit in his talk about having user-defined literals for compile time strings, and how there are some compiler extensions which allow this, but it's not in the standard. And this brings us somewhere in the kind of ballpark of getting this functionality that we need. The future would be having actual string manipulation utilities at compile time. I mean, C++ doesn't really have very good string manipulation facilities for runtime, so we're maybe a ways off that, but we'll see. Metaclasses. So how many of us are familiar with metaclasses? About half the room, maybe? That's cool. So metaclasses are somewhat controversial. This is somewhat maybe a little bit downplaying it. But this is a feature which is being proposed in C++ standards at the moment by Herb Sutter. And it's a way of kind of extending the metaprogramming facilities of C++ into manipulating the actual types that we're writing using code. So I don't know if any of you are familiar with Lisp, but in Lisp, such as Common Lisp, the macro system actually allows you to kind of define your own ways of defining classes. So whereas in C++, classes are built into the language, in some Lisps, they're actually implemented as libraries, because the metaprogramming facilities are so fully featured that you can actually implement an entire language feature as a library. And this brings us some of the way towards that kind of level of metaprogramming. It doesn't take us quite to the extent that Lisps have, and I think that's actually a good thing. But I'll go on to explain a bit about what metaclasses are. So if we have this class called shape, this is going to be an abstract class, some interface. I know probably a lot of us don't like having this virtuals or runtime dispatch at all, but this is just a motivating example. So say we have a shape class, and we have a few member functions which are doing things like getting the area, doing some scaling, and the actual implementation of your subclass is going to determine what these functions are actually doing. So we should only have virtual functions. They should all be pure virtual. We need to have a virtual destructor so that we make sure that all the destructors are called for derived objects. And we need to be careful not to write any private functions or member data or things like that. But none of this is going to be enforced by the compiler. This is all probably going to be enforced through code review or something like that. If I submit this and it has some data members and someone says, well, this isn't really the kind of interface that we're looking for. So what metaclasses allow you to do is something like this. So now, instead of saying we have a class shape and we have this kind of interface-like abstract class just by convention and by trying to do the right thing, we instead say we have an interface called shape, and it has a couple of member functions called area and scale by. Now there are I think two important points here. One is that the code on the right should be entirely equivalent to the code on the left. The second point is there is no interface keyword. So this is not something which is going to be baked into the language, because this is kind of a narrow feature. It's useful in some areas, but not kind of broadly applicable to everything in C++, such that it would be important enough to standardize this interface keyword. What we actually do is we implement this interface thing as a library feature. So this is what interface could look like. So it's a context per function which takes a target type and a source type. If you watched the original videos of Metaclasses, this syntax might be new to you. This is the most recent proposal. But the idea is we're taking some source type and we're using it in order to generate a new type. So we have some nice diagnostics here. So we're saying compiler.require. We're telling the compiler that this is some aspect of the class that we're mandating has to be there, or some kind of restriction on this source type. So if our source list of variables is not empty, i.e. we've declared some member data in our class, then we're going to get a compiler error, and it will say, oh well, you're trying to define an interface, and interfaces may not contain data. So we get a nice diagnostic as to what went wrong. This is relying on some reflection features, well, static reflection features, which aren't quite in C++ yet, but there's a lot of work moving towards them. We can actually then loop through all of the functions which are defined or declared in this type. We can say, oh, you shouldn't have copy constructors, you shouldn't have move constructors. We're going to make everything public by default. We're going to make everything pure virtual. And then the weird syntax is this arrow into target f. And this is code injection. So this is saying we've manipulated this function f, maybe by making it pure virtual, by making it public, done some kind of transformations on it, and now we're going to inject this function into our target type. So this is actually manipulating the target type by adding functions into the definition in library code. Better. Yeah, so I think that in this case, I mean, a lot of these diagnostics are built in order to be rich and expressive and actually help the user. So I can't quite remember. There is a prototype implementation of Metaclasses, and I can't quite remember where it will actually diagnose, but I would hope that it's done. Yeah, it should be done when you instantiate the metaclass. So when you're when the compiler is parsing this interface shape thing, then it will give you a diagnosis. Yeah, so the question was, will it be pointing at the interface line there, or the actual place you made a mistake? So that's something I'm going to get to in a little minute, so I'll hold on to that one. Another one, yes. Yeah, so the question is why is target a parameter for this function rather than like the return type, because we're theoretically we're taking in some source type and we're generating a new type which we're going to be returning. I don't know the answer to that. This is probably subject to change as well, because this is the previously the syntax for this was quite different from how it is now, and it looked more like a class definition with some context per blocks inside it, whereas now it looks more like a normal function. So yeah, it might change. I don't know the reasoning behind it being a parameter. And then we see at the bottom here, this weird thing is injecting a virtual destructor. So we can't forget to write a virtual destructor, which is good if we're trying to write this kind of interface class. So this is what a definition of my keyboard metaclass might look like. And even with just this, we actually get something quite powerful. Because this is the description of the keyboard which I showed you earlier. And we're saying that this is a struct called my keyboard. Even just this change, I think, is really powerful. Because we're now saying this isn't just some struct which happens to conform to some implicit interface and I've made sure I've done the right thing. This is saying, no, this is a keyboard description. It's right there in the definition. And if I make a mistake, the implementation of this meta class is going to tell me. So I think this is, as far as like simple changes to the abstraction goes, this is quite powerful. So inside the actual definition of this meta class, I could have things like this. So I can say the source type must have a type called columns. It must have one called key positions. And if you don't have it, the compiler is going to shout at you. And now this is coming to something that Wouter is talking about. So I can say if my rows are not the same size as what I expected, then I can say, okay, each row of key positions must be the same size as what I'm expecting. And then I can use this source location thing. So I'm reflecting on this key positions in this column member type. And I'm saying, okay, give me the source location and emit a diagnostic there. So I think this goes quite a way to, this is the expectation I had earlier. So when I'm trying to say you have an incorrect layer at this place, I think this is how we can get there. We can reflect on these types. We can get the source location. We can tell the compiler, here's where I want you to diagnose. So I think this is powerful. And so that's all that I wanted to cover. Hopefully, you've seen that embedded DSLs can certainly make your code more expressive, meaning that what you're trying to express to the compiler is more at the level of your application logic rather than at the level of C++. I've shown that you can actually improve the performance of your application by using some of these EDSL techniques, and by using templates, making decisions at compile time rather than runtime. Diagnostics, we still do have some ways to go, I think, but hopefully I've showed having a diagnostic at compile time is better than something failing at runtime for a reason that you don't understand. And having the ability even just to say, oh, something is the wrong size is still very, very useful. So hopefully you can go away with some idea of how you might use EDSLs in your own projects, either the ones you're working on now or future ones. Of course, whenever we're using things like this, we have to evaluate the costs. And there are always, as you said, there are always going to be some costs. Do we want to pay the cost of maybe writing an EDSL for our application domain, or learning some EDSL that someone else has written? Is it going to benefit us enough? I think sometimes the answer is going to be yes, sometimes it's going to be no. And hopefully you can also consider how C++ can improve support for these techniques. If you're interested in getting involved in the standards, it is really interesting. There are people doing a lot of really cool things, proposing some wild changes to C++, which are going to change the way that we write code. So you can get involved. You can come talk to some of us are on the committee. I've not been to any meetings, but Ben is, who else is part of the committee? Yeah, a few other people are like, kind of, like we write proposals, but yeah. But you can come talk to us and get involved. If you have any ideas that you'd like to develop more, you can come talk to me. I'll be at the speaker panel, so you can heckle me then. And I've also got some time for some questions now. But the tagline again, that if you go away with one thing in your head, this could be it. The EDSLs let you write code at the level of your application logic, whilst conforming to tight system constraints. Thank you very much.